In this lesson, we're going to look at orbital speed and escape velocity. And here are the objectives. Let's imagine that we have a planet. This could be Earth, and around it we have a satellite moving. And we're going to assume for all of these problems that we're talking about circular orbits, not elliptical orbits. Circular orbits are going to be good enough for our purposes for now. So here's our satellite moving in a circular orbit, and it has a tangential speed of v. We're going to call the center-to-center distance from the center of the planet to the center of the satellite r. And we know from our study of circular motion, in order to move at tangential speed v at this distance r, we need a centripetal force, which I'm going to call F sub r for radius, equal to mv squared over r, where v is the tangential speed, r is this distance from center to center, and m is the mass of the satellite. We also know that that centripetal force is provided by the force of gravity, which from Newton's law of universal gravitation is equal to g, our gravitational constant, times the product of the two masses, the mass of the planet and the mass of the satellite, divided by r squared. Now, notice first that the mass of the satellite cancels, and one of the r's cancel, and we get v squared is equal to gm over r. And this tangential speed I'm going to call v orbit. It's the speed at which the satellite is orbiting the central planet. Solving further, we get that the orbital speed, that tangential speed, is equal to the square root of g, our constant, times the mass of the central planet over r, the center-to-center distance. Again, remember that r is the distance from center to center. It's important to remember that because sometimes problems will ask you for the height above the surface of the planet, which is here, and that's not the distance r. The distance r is from center to center, so you just need to do a little bit of arithmetic to work out the difference. So this tells us that the orbital speed does not depend on the mass of the satellite. Any satellite put at a given distance r above the center of the planet has to have the same tangential speed from this derivation. That's good. That means if you want to put a satellite at a given height, as long as you know the height and then can work out r, you know the speed it has to go. You don't have to then take into account the mass of the satellite. Notice too that this would give us a way of working out the mass of a planet. If we knew the height and therefore could work out r, the center-to-center distance that a satellite of that planet was orbiting at, and we knew the speed or could work out the speed of orbit, then we could then solve for m, the mass of the central planet. So that's a nice use for this equation as well. Now let's talk about escape velocity. Escape velocity is asking how fast do we need to throw or fling an object so that it leaves Earth and it just never comes back. It doesn't orbit, it just escapes completely. So again, here's the Earth, and I'm going to put, let's say, a baseball here on the center of the Earth, and we're going to throw that baseball upwards, and we're asking how fast do we need to throw it so that it leaves and never comes back. We're going to think about this using conservation of energy. We're also going to imagine that there's nothing else in the universe. There's just this Earth and this baseball, nothing else acting gravitationally on them. And as we throw this baseball outwards, we are going to be swapping its initial kinetic energy for an increasing potential energy as it gets further and further away. And we want to find the minimum speed that we need to throw it so that it keeps going and never comes back. To keep going and never come back in this situation, it would need to get to a point where it is no longer feeling any gravitational attraction. In other words, it is infinitely far away from this planet, otherwise this planet would pull it back. So by definition, at infinity, the potential energy is zero. That's where we've set our zero for potential energy. And because we want the minimum speed, we effectively want it to coast to a stop at infinity. Now that doesn't make sense really, it's never going to get to infinity, but just think of it that way. We want the kinetic energy at infinity to be equal to zero. So we have potential and kinetic energy equal to zero at infinity. What about at the planet where we start? Well, we know that our kinetic energy is going to be maximal here. As we throw it away, it's swapping kinetic for potential energy as it gets further from the center of the planet. So kinetic energy here is greater than zero, but potential energy is less than zero. It's a gravitationally bound system, and we've seen that the gravitational potential energy in a situation like this is negative. Let's get more specific. The kinetic energy is given by 1/2 mv squared, and I'm going to call this v escape. This is our minimal speed that we need to throw this baseball at for it to escape and not come back. And that's our formula for kinetic energy. And from our formula for potential energy, we know that potential energy is equal to negative g times m times little m over r. In other words, potential energy is negative in this situation. And we've said that we want it to coast to a stop at infinity, so the kinetic energy is zero at the end of the problem, as it gets infinitely far away. And the potential energy is also 0 because it's reached our reference point where we've set potential energy equal to 0. And now it becomes a conservation of energy problem. So by conservation of energy, the sum of the kinetic and the potential energy at the start, 1/2 mv escape squared minus gmm over r, so adding our kinetic and our potential energy, is equal to the sum of the kinetic and potential energy at the end. Working algebraically, I'm going to bring the potential energy to the other side, and once again we see that the mass of the baseball here, that's our little m, cancels. We're left with the mass of the planet here, but the mass of the baseball has canceled. And solving, we get that our minimal escape speed is equal to the square root of 2 times g times big M, the mass of the planet, over little r. Little r here being, if we're starting from the surface of the planet, the distance from the center of the planet to the surface, or to wherever we're throwing the baseball from. And as we've seen, the mass of the projectile here cancels, so whether it's a relatively small baseball or a very massive rocket, it doesn't matter. It's going to have the same escape speed for a given r, a given distance from the center of the planet. Alright, let's use that formula now to find the minimum speed for a projectile to escape Earth. We're going to take the mass of the Earth as equal to 5.98 times 10 to the 24 kilograms. And we're going to take the radius of the Earth as equal to 6.38 times 10 to the 6 meters. And now we just plug it into the formula. So our escape speed is equal to the square root of 2 times g times the mass of the Earth over the radius of the Earth. We're assuming that we are flinging this projectile from the surface of the Earth, and that's equal to 2 times 6.67 times 10 to the negative 11, our gravitational constant, which has units of Newton meter squared per kilogram squared, multiplied by our mass, and divided by our radius, and then all square rooted. And when we put that into a calculator, we get approximately 1.118 times 10 to the 4 meters per second, or converting that into kilometers per second, we get approximately 11.2 kilometers per second. So that's the escape speed. Now that seems like a very fast speed. You might be thinking rockets are leaving Earth and are not being pulled back, and they're being shot upwards at much less than that. But remember, this is for a projectile. So in this case, once it's flung or thrown, there's no further force acting on this other than the force of gravity pulling it back down towards the surface of the Earth. In contrast, rockets have a continuous force pushing them upwards, and so they can get out of Earth's orbit, out of the influence of Earth's gravitational pull at much lower speeds than this, because they continue to apply a force throughout their flight. So that's a look at orbital speed and escape speed.